Okay, let me give you guys some practice now. So find the directional derivative of this surface in this direction at this point. So what you've got here is you've got a sphere of radius 10, and then at this particular point, which is right here on your XY domain plane, so you're going to join this point to the edge of the sphere, which is from here to here. So you can see that this is -3 down and +4 across. So that's your vector here. So find the directional derivative at this particular point in this direction. Okay, so press pause and have a go. Okay, so to do this, the first step is you create this thing here, which we're going to mention it as time. So as time ticks away, our particle should start here. And then as time ticks away, the particle moves along. So you've got a function looking like this. For a given time, the time will then determine the x location and the y location of the particle. So when time equals 0, the particle will be here, and then time ticks away, the particle will be here, and then it 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 will be here. You can see it's moving in our intended direction. So once you know the x and y location, then you can put it into the function, and then it will spit out the height. And our job is to find dz by d, in our case ds, because we want to reference everything in terms of s, the path along our intended direction. We don't want to use time. We're going to abandon time and replace it with s. So let's start. So the first step is to set up our particle. So our particle will start at this location, and then one increment of time. So one increment of time. Currently we want it to move across 4 and then down 3. So when t equals 1, you can see that the particle starts here and then moves to here straight away. So what that means is, going back to here. You've got your vertical sheet of paper looking like this in that direction. So the vertical sheet of paper will look something like this. Let's just say the vertical sheet of paper intersects with a sphere along here. Let's just imagine it looks something like this. So you've got to imagine your face is over here looking at this sheet of paper, and your point of reference, as far as you're concerned, the center of the universe is right here. So this is a sheet of paper, it's a 2D sheet of paper, so we can lay it flat. We can lay that sheet of paper flat on the table and then draw our graph. This would be z, and remember this would be 0. When time equals 0, the particle is here. So the center of the universe, as far as we're concerned, is right here. When time equals 0, is here. We should use t, but we're not going to. We're going to abandon t and use s, because we want to use s to reference everything along our intended path. So as the particle moves along, you always know the x and y location. If you know the x and y location, then you can always find the height. It's right here. So when the particle is here, 1 meter across, it will have a height of, let's say, 7. 2 meters across, it will have a height of, I don't know, let's say 6. So 2, it will have a height of 6. When s is 3 meters in 3 meters along this path, it will have a height of, let's say, I don't know, 4. So our curve will look something like this. So we want to find out the gradient right here. Okay, when this is 0. So hang on. So going back to here, this is our z graph. Hang on, z is like this, And when time is zero, you can see that the particle is right here, which means when time is zero, we are looking at this point here, right here. So we want to find the gradient along here. That's what we want to find out. So the thing is, at the moment, the way this is currently set up, is that one increment of time, we would have moved from here to here. So which means, hang on, using Pythagoras, this is 3, this is 4. So using Pythagoras, 3 squared plus 4 squared equals the hypotenuse squared. So the hypotenuse turns out to be 5. Well, one increment of time, it means that the particle has moved a length of 5. But we don't want that, because what that means is one increment of time, our particle would have moved 5 meters across. Another increment, our particle would have moved 15 across. So what that means is this, hang on. What that means is this. We've got a vertical sheet of paper. One increment of time, you would have traveled 5 meters along here. Another increment of time, it would have traveled 10 meters. Another increment, 15, and so on. Each increment of time, we would have moved 5, but we don't want 5. We want to set it up. We want to set up the system in such a way that one increment of time means we move 1 meter across. Another increment of time, we want to move it 1 meter across, and so on. So really, this journey should take 5 seconds because of the magnitude of 5. So we want it to tally up with this. One increment of time, it means you would have moved 1 meter across. Another increment of time, you would have moved another meter across. Another increment of time, you would have moved 3 meters across. We want this t to tally up with this s, the distance in which we're moving along our intended path. So the point I'm trying to make here is that you have to divide by the magnitude. So here you've got your vector. Here you've got your vector. You ultimately want your unit vector. So if you want the unit vector, you've got to get your vector divided by its magnitude. So when you get to this stage here, well, using Pythagoras, this has a length of 5. So you divide this by 5, and you divide this by 5. So this really is your unit vector. This is why in the future we are going to always need the unit vector. Anyway, so using the unit vector divided by 5, that will then give us these parametric equations here. Okay, so what that means is one increment of time, you would have moved 1 meter across, another increment of time, another meter across, and so on. So your function diagram would now look like this. So originally this was t. So for any, we would use t to drive our particle. So as t ticks along, we always know the x and y location of our particle. And then from that, once we know the x and y location, we can work out the height. We can jump to the surface by using this. We can always jump to the surface by using this. So hang on. So now we are currently here. So our function diagram will look like this. This is z here. This is z here, and we abandon t and use s because we want to use s to reference along our particular path. So we abandon t, we no longer use t, we are going to use s. So let me think. So now if you want to find the change in the height with respect to the distance in which we're moving along our particular path, we would use a chain rule. So remember, this is a chain rule. If you look at this, two functions coming in, two variables coming in and one going out, so that means it's got to be partial with respect to x. And then if you look at this bit here, that's us moving to here. Remember, we abandoned t and used s. So if you look at this bit here, that's this bit, that's this function here. So what you've got here is in effect a function looking like this. One input of s, it will spit out one variable, x, the x location. So this is standard d as opposed to partial d. So one going in, one going out. So here, when you look at this, there are two variables coming into the machine, and then it spits out one. So this is partial, this is normal D, because there's only one coming in. Anyway, using the chain rule, and this has to be a standard D, because if you look at this machine here, I don't care what's happening inside this machine, but one's going in and one's going out. So that's normal D, normal D. Okay, so anyway, the chain rule is here, and I will continue in the next video. Okay.